I think since around maybe 15 years there is this emergence of a field in chemistry that is now referred to as systems chemistry. And this is a part of chemistry that is really interested in discovering how properties can emerge from, let's say, complex chemical systems, which are mixtures of molecules that can interact and react and develop properties that cannot be ascribed to a single molecule. And most sciences, they are sort of very familiar with studying complex systems, physics, also sociology. You know, they are familiar with studying complex systems. And from that point of view, chemistry is sort of an exception, because chemistry started out as a science. It separated the compounds to study their properties. In Dutch, the Dutch word for chemistry is scheikunde, which means literally translated the art of separation. So it is considered an art to separate molecules and study the molecular properties. But it's evident that if you separate molecules, you can never identify an emerging property that derives from the interaction between molecules. Okay, so from a conceptual point of view, for a chemist, it's really a change in mindset to start studying complex chemical systems, because it is something contrary to what we've always been doing since the birth of chemistry. And there's a strong two origins in this field. One is because it is related to understanding how life emerged on Earth, so the origin of life. And the other is there's this technological development into making materials that are sort of intelligent and can display life-like materials. So these two pillars come together in this field that is systems chemistry, and that is a sort of very fascinating area that we also got involved in. So there is this other component that's very much related to developing something that can be recognized as synthetic life. And this is basically would be considered a synthetic system that has the characteristics of a living system, which is the metabolism that we are interested in, particularly the energy consumption. But it also needs to be a system that can self-replicate itself, can make its own constituent molecules, can evolve, so can sort of change its information contents from one generation to another. And in addition to that, it has also to be compartmentalized, so it has to be occurring in a certain closed environment. Now, in the last years, in all these separate areas, there's been an enormous progress, and individually, most of these items, I think they can now be, let's say, observed in entirely synthetic molecules. Now, the big challenge is to combine all those elements into one system. I think that's the current state of the art, is to really see if you can make something synthetic, so with synthetic molecules, abiotic molecules, that can incorporate all those different elements into one system. And maybe that is then something that we can start recognizing as an artificial life form, a synthetic life form. I think our main source of inspiration is nature, because nature shows us how non-equilibrium systems work. Only those systems are typically very complex, so you have to look behind the complexity or through the complexity of those systems and see whether you can sort of understand the physical organic principles of those systems. We are now at a stage in which we sort of understand those principles, and we're trying to implement those now actually by making very simple molecules that can sort of display the same behavior that biological systems can do. The advantage of doing that with, let's say, synthetic molecules is that the complexity can be much smaller, so the molecules can be very simple. And the advantage is that it allows you really to understand all the processes that are going, so they're much easier to study, so to say. Examples that people are working on is developing materials for soft robotics. So you can maybe make materials that can, upon cues, pick up something, release it, process information, release at different positions. And this is something that requires something that is referred to as physical intelligence. So in that material, there must be some kind of chemical mechanisms that allow the system to autonomously process the environment and do some kind of action. So you can imagine that there is going to be a completely new kind of delivery systems, for example. One other interesting material is our brain. Brain is also a soft material that has an enormous capacity to, let's say, process information. The challenge is there to make, let's say, synthetic materials that can, maybe in a related way, do something similar. So you would sort of make, the idea is to make some kind of material that can do computing in a similar way as our brain does. And this is also very, let's say, promising target, let's say.